right, thanks again for everyone for joining us here today. My name is Jim Rodarte. I'm the Strategic Marketing and Key Accounts Manager here at AP Tech. And today we're doing episode 4 of our webinar series, and we're talking about pump sizing and product delivery for any application. Evan Sturm is going to be giving the presentation today. I'll let Evan introduce himself in a moment. But at the end of the presentation, we will open it up to Q&A. So if you have any questions, please just enter those in the side, and I'll keep track of the questions as they come in and make sure to get them to Evan at the end of the presentation. On to you, Evan.
Thanks, Jim, for the introduction. Good afternoon, everyone. My name is Evan Sturm, technical sales specialist here with AP Tech. Been in the water treatment industry now for about 5 years, and pump sizing is definitely one of those topics that, in my opinion, is just as critical as the chemistry, just because it is important to be able to dose the appropriate amount, but also being able to dose it in an appropriate manner, more so on a time frame, and being able to precisely dose it as well. So let's just dive into it. The topics that we want to be covering today is why pump sizing matters, typical applications and where you're going to be using chemical pumps, dosing pumps, the types of feed strategies, types of pumps, point of injections, and examples. So we'll go ahead and dive into it. So why it matters. Pump sizing is very important when it comes to mass balance. Mass balance is, I think, the principle to water treatment, and basically what mass balance is talking about is the requirement of product or chemistry needed for that particular application. As water treaters, we're typically used to parts per million, understanding that 120 parts per million is 1 pound per 1,000 gallons of water. So on any of the products that you're using out in the water treatment world, they're going to have an application dose rate when it comes to either continuous or when it comes to shot dosing. They're all going to have different specifications, and that's for any type of chemistry, whether it's liquid or solid. So in order to ensure that you're doing a proper job or a proper treatment and doing it responsibly, you need to be carrying out mass balances to ensure that you are feeding the appropriate amount of chemistry. And you're obviously going to be testing and verifying that with your drop test or colorimeter testing, or even doing ORP, simple stuff like that. That is ensuring that your mass balance was done properly. And if it wasn't, then you adjust accordingly with your pump. The other part is your chemical delivery time. So particularly with shot dosing, we're wanting to slug in a bunch of chemistry very quickly. So it's kind of has the tidal wave effect. But if you're doing it, if you're, so let's just say with a biocide, if you're dosing that biocide, if you're needing to get 5 gallons of biocide into the system, but you only have, let's just say, a half gallon per hour pump, well, it's going to take you 10 hours in order to get that 5 gallons in. So you want to make sure that you have the appropriate size chemical pump in order to deliver that chemistry in an appropriate time frame. The other part is the life of equipment. So in electronic world, there's a thing called duty cycle. And so duty cycle is very important to take a look at, because that is basically a spec on that pump, telling you what that pump can do for how long in a certain period of time. Usually it's a percentage. And so if you typically want to stay on the lighter percentage of duty cycle, so staying within like the 30% range of that pump, because if you're demanding that pump to be pumping full bore for hours on end every single day, and it basically only gets maybe a couple of minutes break here and there, that pump is probably going to be, the lifespan of that pump is going to be diminished very rapidly. And so a pump that might last for 5 years might only last for 6 months. So it's very important that you're looking at all three of these points when looking at chemistry, and when it actually is particularly looking at what type of chemistry you're going to inject and how much and how quickly. So moving on to pump sizing, we're going to go into the applications. So typically with the chemistry that AP Tech sells, with solid chemistry, we're looking at cooling systems and boiler systems as well as closed loops. But on the cooling side, we're typically looking at 3 different types of chemistry: scale corrosion inhibitors, biocides, and dispersants. And then there's those typical point of use items where it's like online cleaners or passivation chemistry, where you're not feeding that chemistry continuous, or you're not running a program using that chemistry for years. It's typically done on a short time frame. On the boiler side, you're looking at all-in-ones, internal treatment, oxygen scavengers, condensate treatment, and alkalinity boosters. All those chemistries are going to be different in their compositions, what type of product is going inside of them. Specifically, like all-in-ones, those are going to have some alkalinity boosters, so caustics. They're going to have sulfites in there, and amines, so volatile compounds. And so those are, products that you need to understand the chemical properties of them to ensure that you're choosing the right pump. When it comes to an internal treatment, like a polymer or phosphate product, they're going to be not as abrasive or aggressive on those chemical pumps as, let's just say, like the alkalinity booster or condensate treatment would be, which is your amines. Jumping back up to the cooling side, the same goes with biocides, because biocides we know are can be corrosive, and they're also can generate gases. Those are particular the oxidizing biocides. So you want to make sure that you understand what chemistry you're using and what is needed on the pump side, because you're not going to use the same chemical pump for your biocide that you would for your scale and corrosion inhibitor. Mainly because biocides, you're dosing at a much lower dose rate, anywhere from like a 1 part per million all the way up to maybe 5 parts. Unless you're doing a disinfection, then that's a different situation. But for continuous feed or just a continuous running of the program, they're typically at lower dose rates as a scale and corrosion inhibitor would be, where the scale corrosion inhibitor could be 18 times the amount of volume that you need in order to provide an appropriate residual. So again, those are things that you need to take into consideration when choosing your pumps. So feed strategy, typically what people do are going to be a continuous dose. So continuous dose would be something that, let's just say you have a chemical controller that you can slave to a water meter. So every time that water meter passes 10 gallons or 100 gallons, typically, it's going to send a pulse to that chemical controller. That chemical controller is going to register that pulse, and it's going to dose an appropriate amount of product for that specific volume of makeup water that was brought into that system. So whether that's a boiler or a cooling system or even a closed loop system, what's the mass balance. So what is required for that 10 gallons or that 100 gallons to treat that volume specifically, how much or how long that chemical pump needs to stay on for. That's typically what a continuous dose is, or a continuous dose could be just a low level dose that every 30 seconds you're going to send 1 pulse, and you're just adding the chemistry because you just want a little slight residual of whatever the chemistry is going to be in that system. But on the continuous dose too, you could also have chemical pumps slaved to ORP. Using oxidizing biocides, those are what you're using ORP for, oxidation reduction potential. And so you're basically you have a set point, and you're feeding that chemistry based off of your set point. So the chemical controller is going to monitor, and it's going to dose chemistry appropriately. And then you also have PTSA, which works, same. You have a set point and the sensors measuring the fluorescence of the tracer that's included in the scale corrosion inhibitor specifically, and it's going to dose that chemistry according to what it's seeing and what it needs to be. Slug dosing, typically that's reserved for biocides, oxidizing or non-oxidizing, either or. And that is when you're basically injecting a bunch of chemistry all at once, and you're only doing this maybe once, twice, 3 times, maybe every day. It just really depends on that system and what are the needs of that system. But you're feeding 1 time a day or 1 time every other day a large amount of chemistry to as I said earlier, that tidal wave effect to provide a good cleaning to knock out any type of bacterial issues or algae issues that you might have in that system and to suppress it. So, how you choose these pumps, or, what feed strategy you choose is going to affect the amount of pump you need, because when you're slug dosing, you're trying to add in a bunch of chemistry at once. So, if you have, let's just do a quick example. You have a 10 part per million residual that you need for your chemistry to add in a slug dose and a 5,000 gallon system. You could be looking at an upwards of a half pound of chemistry that you need to add inside of that system. So you're going to need a lot of chemistry to go in very fast. Whereas with a continuous dose, you might be only looking at a 0.2 part, or excuse me, a 2 part per million dose. So the requirement of the chemical pump is going to be a lot less, is where I'm going at with that. So really, it's how your strategy, or what strategy you're choosing, is going to affect the type of dosing and how rapid of a dose you need. So getting into the different types of pumps, typically there's 3 as water treaters that we will see, but mainly there's only a couple that we see most of the time. The first one, which you don't see often, but is definitely out there, is called the adductor. If anyone has worked around brine tanks, water softeners, an adductor is very similar to a brine tank setup, where you're having the water softener pulling a vacuum, which is then pulling your brine and pulling in the brine solution into your resin bed in order to provide that regeneration of the softener. So in this example, though, the adductors we use are pulling in chemistry. So in this adductor on this picture here, this top port is actually going to be your chemical solution input. So here's where your freshwater makeup is. And as fresh water comes in, there is a venturi down here, which with the venturi effect is going to have a low and a high pressure zone. And that low pressure zone is where it's pulling in your chemistry. And your chemistry gets pulled in, and then it gets ejected out into the system. Adductors work well because there isn't any really moving parts. The only moving part would be a valve on the water inlet side, because once that valve opens up, then the venturi effect starts happening and product is pulled in. Adductors will very quickly inject chemistry into the system at the rate of a gallon a minute sometimes. So it's very fast. So large systems can definitely benefit from this, because adductors are actually much cheaper than a larger chemical pump. Large chemical pumps could be in thousands of dollars, whereas an adductor is not even half of that. So adductors are very economical, and they do provide a means of getting chemistry in there. The only con to adductors, though, is that you need a differential pressure. Because these are relying on high and low pressure zones, you need to have a differential of pressure. So on your incoming water side, typically what we specify is that you need at least half or 40 psi greater on this side than where your injection point is. So what I mean by that is, if your system you're injecting to is at 40 psi of pressure in the system, you need to have at least 80 pounds of pressure on your makeup side in order to actually get that chemistry into the system. If you don't, you will not inject chemistry. So it's very important to take note of that. Next on the other is the peristaltic pump. A very common economical pump. It works really well. Essentially, it's just a flexible tube inside of this housing that has little rollers, and those rollers are squeezing the tube, picking up chemical, squeezing it, so compressing it, pressurizing it, and pushing it out. They work. They do require maintenance, just depending on how often the chemical pump is moving. Again, that goes into the point of looking at longevity of the pump. You don't want this thing continuously spinning around and around and around, because it's going to wear out that tube very quickly. The tubes are cheap, but you don't want to leave, on June 1 and then come back July 1 and this pump ruptured halfway through the month and spilt out all your chemical on the ground. It's not very responsible, and it's not very economical to have that happen. So You want to make sure that you do keep these tubes on hand so that when there is a rupture, it can be replaced very quickly and you can get that system back up and running. Other than that, the peristaltic pumps are very simple. You basically have an adjustable style where it can actually turn up and down the frequency of that stepper motor inside, so you can make it go faster or slower. Or there's just the other ones that are the dumb ones, quote unquote, that you just plug them in and they're just going to put out a continuous volume. So, the adjustable ones are nice because if you have those times of months where you need more chemistry or less chemistry, you can dial it back. Makes it a little bit easier that way. But the other one, which is probably the most common that everyone sees, is a diaphragm pump. There's many different manufacturers, different styles, different compositions of these types of pumps. And they work very well. They're great because they can generate high pressure. So in applications where, like in an amine product where you're injecting into a steam header and you need a lot of pressure to overcome the steam header, these diaphragm pumps are offered in a couple hundred PSI variations where you can get into that high pressure and inject in there, as well as for like the cooling tower sides where you have a mechanical room located in the basement and you have a 400-foot tall building that has a cooling tower on top. Well, that's a lot of gravity or head on those water lines in the basement. So you need a lot of pressure to overcome in order to inject your chemistry. So that's why diaphragm pumps are pretty favorable on that. The other variations of diaphragm pumps are degassing or gas off heads, typically reserved for biocides, because oxidizing biocides and biocides in general, they can gas off, and what that can cause is a airlock inside of the pump head itself. And so once you have that airlock, you're no longer pumping chemistry. So it can be frustrating, but once the gas off pumps came off, that was a great thing for them. So going to point of injection, this is a very important part. You need to understand where you're injecting your chemistry so that it's effective. You obviously want to inject chemistry after sensors, because when chemistry is injected and it goes past those sensors, it can give you false negatives or positives. It can just cause some really wacky things like increased conductivity over, just things like that. But typically what we're talking about point of injection is atmospheric or pressurized. So, sometimes you have applications where you mount a pump on the ground floor, and then there's a mezzanine above your head that has an open atmospheric tank. So yeah, it's open atmosphere, but the pump's on the base or on the ground. So you got to pump up, let's just say 20 feet. So there's just a little bit of head pressure there, but not much. A lot of chemical pumps will be able to overcome that head pressure. But the pressure rod line, so you really need to take a look at what your pump is rated for pressure wise, and as well as how much volume at that pressure, because a chemical pump can be rated for, let's just say 150 PSI, but as you go up in PSI, so let's just start at 50 PSI, you're going to have greater volume pumping capabilities at 50 PSI than you were to at, let's just say 100, the pump was rated at 150 PSI. The volume that it can pump at 150 PSI is going to be less than it is at 50 PSI. So you need to make sure you understand your pressures in these recirc lines, so that you can dose the appropriate amount of volume. The other style of feeding, and is one that we have the capabilities of one of our dissolvers, is the gravity feed. So with gravity feed, it's pretty neat. I mean, it's not a pump, but in my opinion, I think it's important to discuss here because it is another way of dosing chemistry. And if you have the capabilities of doing it, this is the one I completely recommend because it's simple, it's very economical, and it is very effective. These would be, in this example that I drew up, this would be our dissolvers here. And essentially they all have a relay plug on them that can go into your chemical controller. So each one of these will be independently controlled. In this example, we have a scale corrosion inhibitor, biocide 1 and biocide 2. On the bottom of the dissolvers is two ports, and they're tied together, and a tube is dropped down into your in-floor sump. So we're just dropping solution by gravity. When the chemical controller says, hey, open up relay 2, it's going to energize that relay, opening up a solenoid, spraying product, and the chemistry is rapidly dispensed into the basin or sump of your system. So it allows you to get that chemistry in there, circulated, and working as it should be. Typically, these dissolvers are actually cheaper than a lot of the chemical pumps. Very little to no maintenance, and they work actually very well in applications where you want to mount a chemical system on the side of a cooling tower. There's people that mount these on the side of the towers, punch a little hole through the exterior and drop a line into the sump of the basin of the cooling tower, and they provide treatment that way. Because the feed lines are emptied by gravity, those lines will drain out once you're done feeding chemistry. The only thing that you just need to take into consideration is freeze potentials on your makeup water for the dissolver. Outside of that, it's a very basic but simple and effective unit. So here's kind of an example. I just wanted to touch base on this to show you, the demands, and this is going into the mass balance. This is what I would call a fairly proper survey that would be performed at any time you're either acquiring a new account, or even if you have let's just say a rep changeover. Bob was the previous rep and now Jim's going to be the new rep. Jim should probably perform a survey just to make sure, he trusts Bob, but he just wants to make sure that they're doing the proper mass balance. So in this example, we have a cooling tower of certain tonnage operating at a certain percentage of load, 65% that is. So total effective tons are actually 195. And then that goes into the operational side of, what's the delta T from the incoming water to the outgoing water, and as well as what's the evaporation factor. Recirc rate, which is typical 3 gallons per minute per ton of cooling, and heat exchanger temp. So that's wherever the skin temp is of your heat exchangers or compressors, whatever it might be, and system volume. Because if you're shot dosing, you need to understand your system volume to make sure that you're providing a proper dose rate. But the outside of that is just the basic water chemistry. So this is what your makeup water would be like, or what your makeup water is. And then after 4 cycles, this is typically what you would see after 4 cycles, looking at your makeup water. So here is giving us our LSI or RSI so that we understand this system and what, basically where it falls on the scale or corrosive side of things, so that we are choosing the proper product. So in this example, we have 2 different types of feed strategies. The top one is going to be a continuous feed, and the bottom one is going to be a shot feed. So we're going to show you the kind of differences here. In the continuous feed, here we punched in our dosage rates. So at the LSI of the system, our scale corrosion inhibitor is specifying a 34 parts per million as product to be injected into the system. And then with the amount of makeup over the year, this is how much makeup you would have how much pounds you would use per year. For the Durachlor, which is our oxidizing biocide, we are specifying a 2 parts per million dose on the continuous side. And then for our non-oxidizing biocide, a 1 part per million. So with our products, since we're going from a solid to a liquid, there is a concentration. And it's actually pretty simple with our scale corrosion inhibitors to understand what the concentration is going to be like. Essentially, all you do is you measure the conductivity of your makeup water. And then once you've made down solution, so you loaded up your dissolver and you dissolved chemistry, you're going to measure the solution conductivity. That solution conductivity is going to be greater than your makeup conductivity if you dissolve the product. You subtract the 2, and then you're going to get your difference in conductivity. And for every one of our products that we have, we do have a solution strength chart that will specify what's the percentage of concentration. In this example, we have a 0.75 concentration. This is done by design, and why our solutions are lean. It helps with the safety of the system or with the program, so that we're minimizing risks to users of the systems. But we have a low concentration here. So because we have a low concentration, we do need some larger volumes of solution to go into the system. So in this example, at 34 parts per million, we need 7.6 gallons per day of pump. Typically, we're going to specify a little bit bigger pump because, in my opinion, it's going to be cheaper to get just a slightly bigger pump out the gate versus down the line as your customer grows, because we all want growth. As your customer grows and cooling demands increase, if you already taxed your 12 gallon per day pump, then you got to buy a new pump, and now you have bought 2 pumps. So it's better to buy the bigger pump, and also it goes back to the duty cycle. You don't want to, if in this example we're specifying 7.6 gallons per day, if there's an 8 gallon per day pump out there, you wouldn't want that, because that chemical pump won't turn off, and it's just going to keep pumping and pumping and pumping. That goes back to that duty cycle. You want to get that chemistry in there fast, and you don't want to be running that chemical pump all the time. So that's why we're specifying here a 2 gallon per hour pump. Same goes with all the biocides. But going down to the shot or slug dosing of our biocides this time, in this example, we're specifying 1 addition of oxidizing biocide every single day of the week, and then 1 addition of non-oxidizing biocide 3 times a week. And in this example, since we're shot dosing, we need a higher residual in order to build up the concentration inside of the system. So we have 4 parts per million and 2 parts per million versus the 2 and the 1. So now our solution demand has gone up significantly compared to our continuous feed. So this is just, a lot of people like to use the slug dosing, but sometimes I think it's good to run the math to see theoretically how much you're going to actually use. And in this example, we actually, by going to continuous on this system, we're able to reduce chemistry by 3.5 to almost 5 times. So you're able to, provide still a good solution, but at a cheaper rate. So it makes it hard for people to try to pull that out from underneath you. Here, an example, this is a system that we're able to capture, showing kind of ORP control. And this is kind of a good example too of sometimes if you oversize your pump or you have that pump tuned too high. In this example, we have our set point for ORP at 250 millivolts. That's what ORP is measuring, millivolts. And as we see our additions down here, this is when our relay is energizing and how long it's staying on for, typically for a few minutes at a time. You can see that our set point is down here. So once we get to that 250 millivolts, it's going to dose, but it only has a differential of 50. So technically, it should only be dosing up to 300 and stopping. Well, as you can see, the pump is pumping in a lot of solution, and so we're actually overshooting. And not necessarily a bad thing, but you could possibly be using too much chemistry. So it's something to really think about. And the other side of it is our PTSA. The PTSA on this system, the pump using there was definitely, we had it tuned properly, and you can see that we had only a differential of 5 parts per billion. So our set point is 100, and we're only going to 105, and it's staying very tight there. So that's just something to think about. More is less sometimes, and so you just got to look at it and just make sure that you're running a valued system. So what I was showing earlier about the pump sizing and whatnot actually came from a lot of this solid guide. This solid guide is actually a new program that we are super excited to be launching. It's called Solid Guide because what we're helping people do is being able to create surveys, provides easy selection guides, and as well as provide our product catalogs and equipment catalogs and calculators for all of our products across the board. And so it basically allows a rep to carry their iPhone or their Android device and just get some basic operational points of tonnage, hours of operation, water chemistry. You punch all that information in, and if there's requirements for certain biocides that you want, it's going to prompt you all these questions that basically once you're done driving it, it's going to give you all of your mass balance on the system, as well as the recommended product, the recommended pump sizing. It basically makes being able to choose solids a foolproof way. And it's going to give everything in a PDF generated file so that you can print that off, take it to your customer. It's going to show you how many cases a year you're going to need. So once you know your pricing, you can price out a program very easily. And basically, how many times you've seen those bids where it's due tomorrow. Well, you can do that very quickly and without the stress of trying to run around and get the information that you need. It's provided here. So It's in the beta stage right now, and we've gotten great results so far with the beta stage. As you can see the previous slides, we definitely are able to generate some great data, and we're getting ready to release that in the next month or two. So we'll definitely be putting out a little press release for that. So everybody stay tuned for that, please. So that kind of wraps up the pump sizing. I hope I didn't ramble on too much or put anyone to sleep, but again, I find it very important and something that deserves to be discussed about. I hope I was able to maybe provide some useful information for everybody. And if there's any questions I didn't answer, we're going to open that up next.
All right. Thanks, Ian. Appreciate that. We did have a couple questions come in. The first is, where's the best place to mount a pump for solid applications?
Sure. So mounting pumps, typically what we specify is because our dissolvers can be mounted on walls. If you have the clearance height, we typically say to mount that pump below the dissolver. Mainly we do that because what it's going to provide is a flooded suction for your dissolver. So there isn't a chance for that dissolver to suck air, that pump to suck air. So it's really basically you're never going to lose prime in a pump. But there are those applications where you have to mount it above the dissolver, and that's okay because in that configuration, it's like the typical pulling from a drum style. So as long as you don't suck any air, typically that pump's going to stay primed and it's going to work just fine. But our specification is mount it below the dissolver, so you never have those pump issues.
Thanks, Evan. If using gravity, what products work with the Ultra G?
So the Ultra G is actually a pretty awesome piece of equipment because it will feed all of our products. Any of our bottle products to our disc products. Disc products are typically reserved for the scale corrosion inhibitors on cooling towers, but bottle products are basically any of our boiler products and any of our cooling tower products and biocides can be fed inside of this dissolver. Again, just the only important part is you got to make sure that you can feed with gravity. So the unit has to be above the point of injection and the point of injection has to be open to the atmosphere. But yeah, outside of that, every one of our products will be able to fit and be able to be fed in that dissolver.
All right, the last question we have here is, how do you check chemical compatibility for pumps?
So chemical compatibility is going to be determined by the type of product. So first, what I would recommend is looking at the SDS, and all of our SDSs are located on aptechgroup.com. And from there, you can look at the SDSs and see what types of chemistries there are. So basically, any type of alkalinity booster is going to be caustic. The biocides, they're going to be basically a chlorine product if it's an oxidizing biocide, or like a DBMPA or a quat for the non-ox. Those are kind of the more important products that you want to take in consideration. Once you kind of know what what the main component is, you're going to look at the chemical compatibility sheet, which is either online or sometimes provided with that chemical pump manufacturer. And they're going to, specify whether you need to do an EDPM or, some type of either Hastelloy for chlorine products. They're going to kind of point you into the direction of where you need to choose from. But of course, if there is a question that you're just unaware of what chemistry is in our products, we're here anytime to answer questions, and we're going to be able to reach that sales@aptechsolids.com, and we're happy to help you with those questions and answer anything that you have. So.
All right, thanks, Evan. That wraps up the questions. As always, we will be posting this video online so you can share it with your teammates or anyone within your organization.